Okay, it's 9:30. I'm going to start. I'm going to start classes on time. First of all, some announcements. First of all, getting MATLAB on each of your computers to do homework by Thursday should happen. You should get an announcement email from Andrew Chun on, I think it's from him anyway, from one of the LAs, on how to get MATLAB on your computer. It's important that you get the latest version, and you get that from UNC in a way that's described in the email. The MATLAB grader is going to depend on your having the latest version of MATLAB. Any questions about that? There will be an assignment given out probably on Thursday, a first assignment using MATLAB, and so you should have MATLAB on your computer by then. Second announcement, the plan is to meet in person in FB 007, Frederick Brooks Building, room 7, on Thursday. Are there any questions? Okay, so let's get going. I want to start by asking a question about flat spaces, Euclidean spaces, that is to say, spaces where the Pythagorean theorem holds. In a two-dimensional flat space, like the plane where a 2D image lives, what is the simplest orthogonal basis? Somebody speak up.
Just the standard basis.
Yeah, what's the standard basis?
So in like normal Euclidean space, you have a certain number of coordinates, and so it'd just be like 1, 0, 0, 0, 0, 1, 0, 0, 0, and those.
Okay. Okay, so very good answer, but not at all what I expected. And the point is, a vector is not a tuple of numbers. A vector is something with a tip and a tail. It's an arrow. In terms of arrows, rather than talking in terms of tuples of numbers, how many basis vectors are there in a two-dimensional space?
2, like I and J. Is that what you're talking about? The unit vectors?
Oh, well, that's fine. Okay, that's right. So that's what you're saying is there are two basis vectors in two space, right?
Yeah. Mm-hmm.
How many basis vectors in a three-dimensional space?
3.
3, good. Okay, fine. So let's talk about two-dimensional space. Normally the two vectors that you want to talk about, these are so-called the cardinal vectors, are one purely in the x direction. It's a unit vector, and it gets the name E sub x, the unit vector in the x direction. There's another orthogonal vector perpendicular to it, E sub y. Okay, these are vectors, okay? Vectors are things with a tail and a tip. In the case of E sub x, tail is here at the origin. The tip is one unit along the x direction. right? Likewise, for the EY vector, the tip is one along the Y direction, 1 unit along the Y direction, and the tail is at 0. So any vector V into space, the whole idea of a basis can be written in terms of a linear combination of the bases. So I'm going to write A sub x, EX, where EX is a vector, plus A sub y, EY. Okay? So any vector can be written, I guess I'll call the vector A to make it easier. Okay, and it has coefficients of E sub x and E sub y, which are AX, AY, right? That's still a vector. It's something with a tail at the origin, let's say, and a tip at this place up here, which is AX, EX plus AY, EY. Okay, so when we write the original answer, this as a tuple, it's a tuple of those coefficients. That is to say, AX, AY, right? So, okay, so this AX, AY is just a shorthand for, these are the coefficients of EX and EY, the vectors EX and EY. The vector is not AX, AY in the terms that I'm going to be talking about in this whole class. The vector is A, and it's AX, EX plus AY, EY, and its representation is the tuple, the 2x1 tuple, AX, AY. Everybody okay with that idea? Okay, so.
Quick question.
Yeah.
So in this case, we're just sort of stating that EX and EY are orthogonal. There's an orthogonal basis.
Yes.
Is that okay? Gotcha.
Yeah, not only orthogonal, but an orthogonal unit basis. Unit, a basis made up of unit vectors which are orthogonal to each other. Okay? Okay, so how many entries are there for this representation of a two-dimensional vector? This is a very easy question. Someone holler out the number. How many entries here in this tuple?
Just 2 entries, right?
Okay, fine. Now, when I am in 3 space, I have yet another basis that comes out of the page, and it's called EZ. And then the vector in 3 space will be AX, EX plus AY, EY plus AZ, EZ, and EZ is the unit vector orthogonal to the page. And now how many entries are there going to be in the representation of this vector in 3 space?
3.
3, right? AX, AY, AZ. Okay? Okay, so I may write this I may choose to write this tuple as A sub I, meaning A1, A2 if we're in 2 space, or A1, A2, A3 in 3 space, or if you will, AX, AY in 2 space, and AX, AY, AZ. But because we want to have the coordinates be able to be either 1 or 2, we write it as a subscript, or I may decide to write it A sub X sub I. A sub X sub I means, because I'm going to take the convention that X1 means X, and X2 means Y, and X3 means Z if I'm in 3 space. Whoop, off the page. Okay. And so now A sub X sub 1 means a sub x. A sub x sub 2 means a sub y. A sub x sub 3 means a sub z. Okay, in any case, the point is that I can fill in this tuple with various values of the tuple. And for the gradient, well, the gradient in two space then could just the gradient of the image at any point in the at any point in the image could be written di by dx sub I, where I can take on the value 1 for the first entry, which means it's di by dx. I can take on the value 2 for the second entry, which means di by dy. And in two space, or if we're in three space, there's also, I can have the value 3, in which case di by dz. And so this is going to be the kind of notation I'm using to mean the one tensor, an n by 1 tuple, an n by 1 tuple, where n is the dimension. Okay, so for a two-dimensional image, you have a 2 by 1, which is the gradient, which has the first derivative in the x direction in the first place, the first derivative in the y direction in the second place, or in 3 dimensions, it also is a 3 tuple, a 3 by 1, and it has the di by dz in the third place. Any questions at all about that? Okay, now let's get on to two tensors. Two tensors are n by n arrays, where n is still the dimension. It's just like before. If you're in two space, n equals 2, it's a 2 by 2 array. If you're in three space, it's a 3 by 3 array, right? And in particular, for the Hessian, the second derivative tensor, okay, so this first derivative tensor, I write d1 of I, this is a 1, d1 of I is this, and this guy here is going to be d2 of I. Okay, so in 2 dimensions, we write d2i by dxi by dxj. So xi can take, now it gets a little bit confusing because this xi can be x1 or x2, and xj can be x1 or x2. So you have 4 entries, 2 by 2. And so the 1/1 entry is d2i by dx1 by dx1. I equals 1, j equals 1. With the 1/2 entry is d2i by dx1 by dx2, which is to say d2i by dx by dy. The 2/1 entry is d2i by dx2 by dx1, which is to say d2i by dy by dx. And the 2/2 entry is d2i by dx2 by dx2, which is to say d2i by dy squared. Any questions about what I'm saying here? Let's go on to then to d3i. Oh, before we get to d3i, let's talk about d2i in 3 dimensions. It's still d2i by dxi by dxj, but I and j can take on the values 1, 2, or 3 because it's in 3 dimensions. So you get a 1, 1 entry, a 1, 2 entry, a 1, 3 entry, a 2, 1 entry, a 2, 2 entry, a 2, 3 entry, a 3, 1 entry, a 3, 2 entry, and a 3, 3 entry. 9 entries, it's a 3 by 3 two-dimensional array. Okay, it happens to be a matrix, but I'm going to get you to be careful about what we mean by a matrix, because it's not simply an array. But for the time being, you're used to 3 by 3 arrays being matrices. Okay, so this is a 3 by 3 matrix in 3 dimensions, a 2 by 2 in 2 dimensions. It represents the second derivative information. Okay. On to now the third derivative. Okay, so the third derivative is the first thing that should be more or less new to you. It is a 3-dimensional thing, not because not because the space is 3-dimensional. I'm going to talk about a 2-dimensional space, a third derivative information. So it's got 2 entries in each of in 2 dimensions, 2 spatial dimensions. It's got 2 entries in each of the 2 entries in each of the 3 dimensions. And what's in here is d3i by dxi1, dxi2, dxi3. Where each of the x of I1, I2, and I3 can take on the value 1 or 2 for a 2-dimension when we're in a 2-dimensional space. So we're going to have d3i by dx, dx, dx. That's 1, 1, 1. We're going to have d2i by for 1, 1, 2 dx by dy. And 1 1 1 2 1, which is going to be d3 of I by dx. What did I say? 1 2 1, which is dx dy dx, and so on. It's simply 2 matrices, 2 two-dimensional arrays back to back. There's a front one for I equals 1, a front one for the last entry equals 1, and a back one. So it's a 2 by 2 array in front and a 2 by 2 array in back. It's a cubical thing, and every entry has a third partial derivative in there. Any questions about what those partial derivatives are?
Yes, I have a question, Professor. Is it because it's represented in 3D space that we use dx of I1 and dx of I2 instead of dx
It's not in a 3-dimensional space. It's in a 2-dimensional space. But there's 3 entries, 3 subscripts, 3 indices.
Okay.
Be careful. The dimension of this is a so-called this is a 3 tensor. The tensor is got 3. I hesitate to call them directions, but it's got 3 positional variables because it's a cube, but it's for 2-dimensional space. It's a 2 by 2 by 2 3 tensor. It's a 3 tensor with n equals 2.
Okay. So on the other, you didn't, they're not called directions, but you said the other kind of sides out of the 3 of them. Is that where you have dx of j1 and dx of j2?
Yeah, right. So one of the indices takes you from left to right. One of them takes you from top to bottom, and the other one takes you from front to back. And each one of them can be 1 or 2. So there are 8 possible combinations.
Okay, thank you.
Okay, so now,
Sorry, I have another question.
by all
Is there
means,
is there a conventional order of those? Like the first one is left to right, second up and down, third front to back?
yeah, that is the convention, but it's not, it turns out in this situation of derivatives, it doesn't matter. And the reason it doesn't matter is that the derivative values are independent of the order of the subscripts. So just as d2i by dx by dy is the same as d2i by dy by dx, it's also the case that d3i by dx by dx by dy is same as d3i by dx by dy by dx is the same as d3i by dy by dx by dx, and so on. Any permutation of the subscripts of the indices gives you the same value. And because of that symmetry, at least for these derivative tensors, it doesn't matter which entry is which direction is corresponds to which subscript. But good question. Lots of good questions. In fact, every question is a good question. Any further questions? Okay.
So if we're working on a problem like this in class, is this the notation that you want us to use, drawing the cube?
Well, you want to think of it as a cube, yes. I don't know, you can draw it as a cube, yes. Okay.
All right, thank you.
So for the 3 tensor for 3 dimensions, what's the size of the cube going to be? Still going to be a cube, it's a 3 tensor.
3 by 3 by 3.
It's 3 by 3 by 3, right? And each one of the subscripts can be either X or Y or Z, all combinations of 1, 2, 3, will give us 27 entries, right? For this D3i thing. And D4i, the 4th derivative tensor, is going to, I can't draw it. It's going to have yet another dimension. It's going to be a n by n by n by n thing. And the entries in it are going to be D4i by dx1 by dx2 by dx, well, I'll call it xi1, xi2, xi3, dxi4. And I1 can be either 1, 2 in 2 dimensions. I2 can be 1 or 2 in 2 dimensions. I3 can be 1 or 2 in 2 dimensions, and I4 can be 1 or 2 in 2 dimensions. Or in the case of 3 dimensions, I'm going to write this. Oops, big D. In 3 dimensions of space, we have I1 can be 1, 2, or 3. I2 can be 1, 2, or 3. I3 can be, let me write that so it can be readable. I3 can be 1, 2, or 3, and I4 can be 1, 2, or 3. Okay? So far so good. These are the tensors. These are the derivative tensors. The tensor can be any one of these things of that particular size, but for us, the entries are these partial derivatives for the derivative tensors. Now we need to be able to talk about the application of a tensor to a vector. So let's start off with the ones we started off with the 1 tensors, ax, ay, and it's going to be applied to another vector, bxby, whose representation is bxby, with a linear operation. Well, the linear operation is dot product. And so we get ax, ay applied to the vector bx, by, and you get ax, bx plus ay, by, which is a scalar, right? Any questions about that? So apply a one tensor to a vector, and you get a scalar. And we call scalars zero tensors. The zero tensor, which is a 1 by 1, which has ax, bx plus ay, by, when you apply the one tensor ax, ay to the one vector bx, by. That was a plus sign here. Ax, bx plus ay, by. Okay, fine. Now, the two tensor is a matrix. It's also an operator. It operates on vectors. If you have the matrix, any square matrix, let's say a 2 by 2 matrix like D2I is, and you apply it to a vector, all these guys are going to apply to vectors. You get a matrix times a vector and a matrix, or matrix times a so-called a two vector, which is another two vector. That is to say, it is a one tensor. So you start out with a two tensor, D2I, you apply it to a vector, and you get a one tensor. So applying the matrix to a vector lowers the order of the tensor by 1. You start out with a 1 tensor and you apply it, you get a 0 tensor. If you start out with a 2 tensor and you apply it to a vector, you get a 1 tensor. Okay, so far so good. And any questions so far? Well, this 2 tensor might be 3 by 3 instead of 2 by 2. So you apply it to a vector, which is a 3 by 1 thing. And 3 by 3 times a 3 vector gives you a 3 vector. That is to say, again, a 1 tensor. Again, lowering the order of the tensor by 1. Now let's talk about the 3 tensor with n equals 2. It's a 2 by 2 by 2 array. It can be understood as two vectors, one in front of each other. Two matrices, one in front of each other. D3I can be understood as a 2 by 2 matrix with another 2 by 2 matrix behind it. Doesn't matter, by the way. You could also think of it as a matrix, a 2 by 2 matrix on the left side next to a 2 by 2 matrix on the other side. But let's take the first interpretation of a 2 by 2 matrix on the front and a 2 by 2 matrix on the back. And so when we apply that to a vector, we will get, for the front matrix, we apply it and we get a one tensor. For the back one, we get a 1 tensor. That is to say, we have a 2 by 1 thing in front and a 2 by 1 thing in back. And so this is a 2 by 2 thing, which is a matrix, which is a 2 tensor. And so when you apply a 3 tensor times a vector, you get a 2 tensor. Okay, so you just take one of the dimensions away, if you will, and you apply the matrix to the vector for each of those, and you look at the results for each. And the same thing goes for the 4 tensor, right? You're going to have a 2 by 2 array of matrices, and each one is going to get applied to that vector, and that's going to end up giving you, from a 3 tensor, you're going to get a 2 tensor. and on and on. Okay, so now we have the idea that we can multiply a tensor by a vector, and we will get a one lower order tensor. Any questions about that? And then finally, we can take the result of one application to one vector and apply it to another vector. Apply the result to another vector. So if we start out with a 3 tensor, and when we apply it to a first vector, we get a 2 tensor. We can take that resulting 2 tensor and apply it to another vector and get a 1 tensor. And then we can take that tensor and multiply it by yet another vector, and we get a scalar, that is to say a 0 tensor. So if we multiply a 3 tensor times first one vector, then a second vector, then a third vector, we get a scalar. And that's what I mean when I talk about taking application to a tuple of vectors. That is in a 3 tensor, you're going to apply it to a u sub 1 and then to a u sub 2 and then to a u sub 3, where those are 3 unit vectors. And we're going to get a result. Or any vectors, a vector v1, v2, v3, where they're not necessarily unit vectors. You apply it to v1, then you apply the result to v2, then you apply the result to v3, and you get a scalar. And if you work it out, I want to go back to the first answer that was given in class, which was quite a reasonable answer, even though not quite what I wanted. That is to say, these unit vectors are going to be, for example, in 2 space, represented by 0, 1 and 1, 0. And so if you want, and if you want the 1/1 second derivative, you're going to apply to 1, 0 twice. If you want the 1/2 second derivative, you're going to apply to the u1 vector once, and then the u2 vector next. Okay, 1, 0 first, and then 0, 1. In 3 space, it'll be 1, 0, 0, and then 0, 1, 0 to get the 1/2 entry. Any questions about all this? It's conceptually not hard. It's just a little bit mind-bending and keeping track. The main thing not to get confused about is the difference between the order of the tensor and the dimension of the space.
Yes, Professor, I have a question.
Mhm.
So with these, do you have to multiply, when you're multiplying with the vector, does it have to be a vector of the same number of elements of the dimension? Like,
Yes.
okay, so for the 1 tensor, what do you multiply that by? What vector?
Well, whichever vector you want to apply it to. If you're trying to apply it to a unit cardinal vector, then you will apply it to either 1, 0 or to 0, 1.
Okay.
Depending on whether you want the first entry or the second entry. Okay, so the whole point is, if you apply one of these derivative tensors to the appropriate use of i's, the ones where there's a 1 in the place for whose derivative direction you want, then you will get that derivative entry out. Right? You'll get exactly these directional derivatives out. Okay. Quick question. How many entries, for 3 dimensions, the 4th derivative tensor?
3 to the 4th, so 81.
81, 3 by 3 by 3 by 3. Right? 3 times 3 times 3 times 3 is 81. Good answer. Thank you. Okay. Now comes the next mind-bending notion. These tensors are applied at every pixel in 2 dimensions. You get a different value for each one of these tensors, the D1 tensor, the D2 tensor, the D3 tensor, and the D4 tensor. Each one of these tensors, for any given one of them, let's say the 2 tensor, the 2 tensor at 1 pixel is the value of the partial derivatives at that pixel, the partial derivatives of the image at that pixel. You take another pixel. I mean, this may be a 256 by 256 image for the 101, 201 pixel. There will be a value of that 2 tensor. There'll be a different value for the 42, 75th pixel. Okay, so the image has an image of tensors. What's confusing is the image is an array, right? But it's not a matrix. A matrix, in our terms, is going to be a thing that is an operator that applies itself to vectors. An image is not applied to vectors. An image is an array. It's a perfectly fine array. It may be 256 by 256 or 300 by 300 or in 2 dimensions, or 1024 by 1024, or even not even square. But I mean, it may be rectangular. But the point is that it's an array, yes, but it's not a matrix. When I use the term matrix, I'm going to mean an operator on vectors. It is also an array, but its job is to multiply vectors and turn vectors into other vectors, to map one vector into another, or if you will, to map a vector space into another vector space of the same dimension. Questions about that? Okay, so we are basically ready to talk about let me see if I can push the right button so I don't turn this thing off again. Okay, so let's go to basic. All right, everybody okay with this, seeing this PowerPoint slide now? I guess so, since nobody's complaining. Okay, so all of what I just said is on this single slide. The lecture so far: 0 order tensor is 1 entry. It's a 1 by 1 array. A first order tensor is n by 1. A second order tensor is m by n. A matrix, a third order tensor is m by n, and so on. And then post multiplying, pre multiplying. Okay, the other thing that I didn't quite say is that you got to be a little bit careful, because when you finish up, you want, if you want to write it in matrix notation, you want to have a 1 by n times an n by 1. And I'm going to use the convention in this whole class that the representation of a vector is a column, okay? So we talk about column vectors. And so the corresponding row vector is going to be its transposed. And so you need a transposed to take the operand at the end. The rest of them can be on the right, multiplied by column vectors. So when you multiply by a tuple of n vectors, the first n minus 1 of them can be multiplied on the right, but the last of them has to be, it's transposed, multiplied, pre-multiplied. Any questions on that complication?
So just to clarify, when say we have some k order tensor and we're multiplying by some vector, pre-multiplying by the vector, then the columns that we are considering are taking the first entry and iterating over, like the first, say, xi1 or x1, I guess, the entry, iterating over that and then getting the and then from that getting columns with the rest of the entries.
Okay, you will see this better if I go back to my previous page from the camera. Okay, let's look at the 3 tensor. It's a 2 by 2 by 2 array if we're talking about 2-dimensional images. If we're going to multiply by 3 vectors, v1, v2, v3, or then we're going to multiply by v1 as a column vector. So in other words, this matrix, the front matrix, is going to get multiplied by that 2-entry tuple for v1. And likewise for the back matrix. Okay? And so that's going to give me this matrix times v1. The front matrix times v1 is going to give me a result, which is going to be a 2 vector, something with 2 entries. Likewise for the back one. So you're going to get another 2 vector. Okay? That's a matrix. It's 2 by 2. That matrix can be multiplied by v2, the second operand. And when you do that, you're going to get a matrix times times that v2 vector, which is a duple. And the result is going to be another result, which is a 1 tensor. It's going to have 2 entries. The v3, in order to multiply it by v1 using standard linear algebra notation, has to be v3 super t transposed times the result of the first 2 multiplications. Does that answer your question?
Yes.
I thought the example would help. Any other questions? All right. Okay. Now that we've got all our derivatives taken care of, we now know how to take any directional derivative. Now we have Taylor series. Taylor series are at a point. I call it x of 0. Sorry, abusive notation. The 0 now means which place it is, which pixel it is in 2 dimensions. Okay. In 1 dimension, you should be used to the Taylor series. You take the 0th derivative, which is the value of it at the base point, I sub 0. And for each of the other derivatives, you multiply x minus x0 to some power, the kth term. Looks like I got an error here. Yes, I do. Sorry. Let me fix my subscript. PowerPoint. Whoop, wrong one. What a pain. All right. This should be A1. Too many buttons to push. I'm gonna be glad when we get back into the classroom. I don't have this problem. Anyway, fine. All right, back. Can everybody see what I have on the screen here? Okay, so we take the first derivative di by dx divided by 1 factorial and multiplied by x minus x0. Then we add the second derivative d2 by di by dx squared and divided by 2 factorial and multiplied by x minus x0 squared, and so on. Any questions about the one-dimensional Taylor series? It's a prerequisite. You should know it, but I'm happy to answer questions about it. One ordinary Taylor series in one dimension that you have seen before. So now I want to talk about the Taylor series in n spatial dimensions, like 2. Okay, or like 3. But we're going to talk about, let's talk about the 2-dimensional Taylor series. Now these derivative entries, there are 2 first derivatives, there are 4 second derivatives, there are 8 third derivatives, there are 16 fourth derivatives in 2 dimensions, right? And the point is that the sum goes over all the derivatives, all the entries in the tensor. So for the second derivative term, you have a d2i by dx by dx, you have a d2i by dx by dy, you have a d2i by dx by dy by dx, and you have a d2i by dy by dy, and all of them are divided by 2 factorial. For the third derivative term, you're going to have 8 entries. And every one of those entries is used, summed up, and all divided by 3 factorial and multiplied by 8. And moreover, the x minus x0 to the k term also changes its subscripts. So when you're multiplying by, for example, the 1, 2, 3 entry for a third derivative, which is to say d3 by di by dx by dy by dz, you're going to have x minus x0 times x times y minus y0 times z minus z0. So every time you had an x, a particular index of the dimension, 1, 2, or 3 there, you're going to have the corresponding multiplication of terms x, y, or z on the right, right? So you end up with these k tensors used, multiply by the product of the corresponding entries x minus x0 or y minus y0 or z minus z0 in 3 dimensions, or x minus x0 or y by dy0 in 2 dimensions. Okay, so the Taylor series is going to be a 0th order term. I am here, I of x equals I of x0, plus a first order term. Well, the first order term, there are n entries in your tensor, and so there are going to be all choices of one index over the n possibilities. So in 2 dimensions, there are 2 choices, 1 and 2. So you have di by dx and di by dy. The di by dx gets multiplied by x minus x0. The di by dy gets multiplied by y minus 0. Everything is divided by 1 factorial. For 2 dimensions, for 2 dimensions, but a 2 tensor, the second order term, you now have 4 entries. And d2i by dx by dy is, for example, going to get multiplied by x minus x0 times y minus y0. and so on. Any questions about what's going on here? This is the generalization of Taylor series about a position x underline sub 0. The point about Taylor series is that they are the best local polynomial approximation of whatever order you stop at. In the infinitesimal neighborhood about x sub 0. They're very good local approximation. If you choose x sub 0, x underline sub 0 to be the center of some pixel in a two-dimensional image, round about that pixel location in the image, you're going to get a really good approximation. If you choose the base thing for another pixel, it'll be a very good approximation round about that pixel. But if the pixels are well separated, the first Taylor series about the first pixel will not be a good approximation at the position of the second pixel and vice versa. It's a local approximation, and we're going to not be mostly satisfied with just a local approximation. We want approximation that works broadly across the image. But if you do want a local approximation, the Taylor series is just great. Any questions?
Can we have an example of what one of these Taylor series would look like?
Well, okay, so I mean, just if you're about, I need to get myself a camera up. Give me a moment. Button. Screen share. Advanced camera. Okay, so we're talking about a 2x2 image. We have an image that, let's say, is 256 by 256. We have a particular position here that is let's say the 29th row and the 190th column. So we're interested in x0 at the position at pixel is the location x sub 29, 190. So that's x sub 0. And then we're going to say I at some x, which ideally is near 29 location. So it's a little bit of a region about this position in the image, is going to be I at x 29, 190. That's I of x0 plus di by dx at x 29, 190 times x minus x0 to the 1 power over 1 factorial plus di by dy x 29, 190 times y minus y0 over 1 factorial. So that's 1 factorial. Okay, plus d2i by dx squared at x 29, 190 times x minus x0 times x minus x0 over 2 factorial plus d2i by dx by dy x 29, 190 over 2 factorial times x minus x0 times y minus y0, because this xy, of course, means you go this xy. Then there's going to be 2 more terms, d2i by dy by dx of x over 2 factorial times y minus y0 times x minus x0. And there's finally going to be a 4th term, d2i by dy by dy over 2 factorial y minus y0 times y minus y0. And then we go on to the 3rd order terms, of which they're going to be 8, and each one's going to be divided by 3 factorial. Does that example do it for you?
Yeah, thank you.
All right. So okay, so we now have the Taylor series is for each one of these k's, which are the order of the derivative, we have m to the k entries, where m is the dimension. I called it n before. And it's chosen from all the possible entries in the tensor, the corresponding tensor. So for the kth term, you're talking about the k tensor, which is an m by m by m by up to k entries. Okay? I now want to move on to an interpretation of this idea of a Taylor series approximation. And in it, we think of the polynomials. Okay, so consider any one of these polynomials. So for example, the one that we used for the xy term in the 2nd order was x minus x0 times y minus y0. X minus x0 times y minus y0 is a polynomial. It has a value at every position in the image xy. It is an image. And if you evaluate that polynomial at every xy in the image, you will get the polynomial valued image. That is to say, it will be an image in the of the size. If we have 256 by 256, it'll be a 256 by 256 array with values which are the polynomial values at those respective xy's. Okay? It's an image. It's an array. It has values. And the Taylor series is a weighted sum of such images. So just as when we talked about vectors, we talked about the weighted sum of basis vectors. Here we can talk about the weighted sum of basis images. And the basis images are these polynomials that you see in the last line on the screen. They are images evaluated at all the pixels. Of the polynomial evaluated at all the pixels. And its coefficients are the entries to the derivative tensors divided by k factorial. The coefficient of the particular basis image with particular choice of the I sub j's is that derivative value of a k factorial. It's the coefficient of the basis image. Okay, so now we have the notion that the Taylor series is writing the overall image, I, as a linear combination of basis images. And each of the basis images I've got by these polynomials. Questions? All right, so yeah, this is what you asked me to do last time. And I mean, in the example, and it's there, and we cut it off at some number of terms. Okay? And what I have said is that the Taylor series is a good approximation locally and a poor approximation unless you have an unbelievable number of terms if it's far from that image. The other thing to remind you is that we have said already that spatial derivatives of order 1 are going to be used to compute edgeness, and those of order 2 are going to be used to compute barness. How strong a pixel, how strong the information of being an edge is. And you are going to receive an assignment given next time to actually go compute gradients, gradient magnitudes actually, or more precisely, gradient magnitude squared in an image that you choose using these ideas of one tensors producing gradients. Questions? Okay, so this exercise is due on Thursday, right? It has two parts, and it has an example up above, and then it's got two questions at the bottom, A and B. And at the beginning of class, I'm going to bring up somebody's answer, and we're going to look at it. You need to have your answers into Sakai by then, by class on Thursday. Questions? End of the first slide set. All right. On to the next topic. The next topic has to do with shift invariant linear operators. And if I can find it, which I can't, hold on. Let me unshare here. Get rid of some of my screens so that I can sorry for the time it takes to get the right thing on the screen. Here we go. Okay. So this is a new topic. We've done the first bullet, representative images as Taylor series and computation of image derivatives. And now we're going to go on to, first of all, decide what we mean by geometric operators and invariance to them. And then we're going to go on to the particular kind of operator that is very, very common, and that is a linear operator that's invariant to shift, to translation. And we're going to be talking about all these topics underneath this. And this is going to take, like a third of the course. So this first topic is going to go quick. And then this next topic, shift invariant linear operators, is going to actually take us quite a few lectures. Okay? So, and we've said that images are arrays, not to be confused with the kind of arrays that are matrices. And we're going to understand the value of a pixel to be at a value at the center of the pixel. So the pixel is a little square region of space. And we're going to be understanding its value, its intensity to be at the center of that position, to the center of that little square. In 3 dimensions, we'll have voxels. There'll be cubic entities, and we'll understand their values to be a value at the center of these voxels. So we have an array. Let's get the camera up again. Okay, pane, share screen. Advanced. So we have an image, which is a big array. And it has little squares that are made up of it, that it's made up of. And the intensities here and here and here and here are going to be at the centers of these pixels. Okay? So when we look at an image as, for example, 256 values across here and another 256 across here, each one of these guys is at the center of a little pixel region in a continuous image. Okay, but it's sampled at these center points. Questions? But we will sometimes need to have values of the pixels at other positions than these pixel centers. So for example, have to go back again. Takes all sorts of time to keep going back and forth, but we will do it nevertheless. We take these guys and we rotate the image. Then in horizontal spaces, the old pixel values aren't at pixel centers anymore. And so we're going to have to get if I wanted to rotate that one, I'm going to need pixels along things that are now horizontal. Right? And those places are not going to be at the pixel center, the old pixel centers. So I'm going to need a bunch of places separated along there. And those are not going to be old pixel centers. So I'm going to need to be able to interpolate the intensities. And so that interpolation is going to mean I'm going to need a new approximation to the image that is evaluated at these new pixel positions. And there's a motivation for having to have an approximation that we can evaluate, like a polynomial approximation, like Taylor series, but I won't do Taylor series very well because we need a different Taylor series at every place. And so we will need this ability to do interpolation. The other question that we're going to need to face is when we do this approximation, we need to have an adequate spacing of pixels, and we don't know right at the moment how to figure out what the spacing of the original image should be or of the interpolated image. And that's going to be a topic we have to face and we will face. Notice that we've already talked about an image here, which is a linear combination of basis images. These psi k of xy are all the basis images. For the Taylor series, they were polynomials. And each one of the polynomials could be evaluated at any xy. That is to say, you had a formula for it. We say a formula with parameters. The formulas are the coefficients, a sub k. For any xy, you can evaluate I of xy. And so in particular, when you want to interpolate at a particular xy, you just evaluate that polynomial. Just like for vectors, if you have a space of dimension 2, you need 2 coefficients. If you have a space of dimension 3, you need 3 coefficients. If you have a space of dimension 976, you need 976 coefficients. Well, an image has a 256 by 256 image has 256 squared 2 to the 16th values. It's sort of like a vector with 2 to the 16th values. And so you'll need 2 to the 16th coefficients to get a perfect approximation. Geez, we don't want to have to figure out 2 to the 16th coefficients. We really want to get away with 80, some much smaller number. So we're going to be interested in the sum cutting off our sum, which goes up to some number n, from not at the total number of pixels of voxels, but rather cutting it off for some n sub 0, which is way, way, way smaller than the number of pixels of voxels. Okay? Clear what we're after? Any questions? Okay. We will be interested in 2 kinds of approximations. Global, where you have the same set of basis images for whatever xy you're using, you're going to use one set of basis images. We've seen that that's not a particularly good thing when the Taylor series polynomials are the basis images. But we may want to divide the image into, as 2D image, into 4 by 4 subimages. Okay, so we divide the image space into 16ths. And we'll get 16 sets of basis images, 1 for each patch. And we'll be later worrying about this idea of linear combination of a different basis for each patch in the image. So the upper left, I said, if I were dividing it into 4 by 4, then it would be the upper left 64 by 64 would be 1 patch. The next 64 by 64 to the right of that would be another pit patch, and so on. And we'll be worrying about that. But for the time being, we're going to be talking about global approximations. That is to say, one set of basis images that's going to be used for the whole, all locations in the image. So the essential question we have to deal with, and I'm going to stop with this next paragraph, what should be the basis images? What should be the psi-Ks? We've seen two possibilities, actually. One is that the basis images are 1 at the kth pixel and 0 elsewhere. That's just using then the coefficients are just the pixel entries, the values. And we've seen the Taylor polynomials. And both of them are too local. And so we're going to be interested in basis functions that are more global. And that's what we're going to be after now, trying to find a good set of psi-Ks, basis images, that we can write as linear combination of them, and it works well for any position in the image. Questions before we stop? I hope I will see you in the classroom, FBO 07 on Thursday. Everybody masked. I'll be masked as well. I hope we all can stay healthy. Questions before we end? If not, I will say goodbye for now. I remind you that there is an office hour at 2:30 today for anyone who has questions they want to ask. I'm going to turn off the recording right now, but I'm going